Mm. Yeah, maybe I'll do this in parts because I don't want to just spoil it and it's kind of lame. Okay, let's talk about this question in parts because if you just spoil in one go, especially if it's the first one, it's no fun. For you, it's actually pretty fun for me because like spoiling it just makes you like it's like I know the answer, you don't, right? It's kind of like a natural fun thing to do, but like it's not very productive. Okay, but let me just so I think these kind of questions we've seen a few of them, part A, part B's, they're like the kind of questions where notoriously, you can't they're not just like 7 or 0s kind of thing. You can get like 3s and 4s. But I always think it's better to look at both parts before just starting the first part, because you might save yourself some trouble. Especially, I think in general, it's good to like look for like ideas just beyond trying to solve the easy case, even when you're doing the easy case. Okay, so there's two notions here in the question. You have a set of points, and these are geometric points, so they're in a plane. Okay, and there's two properties it could have. It could be balanced, which means any A, B, and S, there exists like a C such that AC equals BC. Yeah, or you use capital letters. So there exists a point that's equidistant from both. Yeah, and it's called center free. If for any triple of points A, B, C in S, that does not exist. So it's not true that there exists a point D such that D is equidistant from all 3 points. Okay, and the first question asks, the first part says, basically give an example of a balanced set for each finite set, like each size of points, yeah? So for each n, one, so is it? Oh, yes. Yeah. Show S with size equal to n exists. Balanced. And then basically B is what's the so whether or not it just claims it exists. The other one just whether or not it exists, yeah. Whether or not determine which n which n there exists an S. So S equals n, and S is both balanced and center free. Alright, so the first part, I guess, I think everyone probably has already done this. Is that if n is odd, and this solves for both parts, yeah? If n is odd, then you can take a regular n-gon, yeah? You said it actually also.
Yeah, I said it. So I thought I didn't have it.
Wow, this memory.
I didn't even write it down. I just thought of it.
Okay, so odd n regular n-gon. Of course you can do it for the small case, but when it's n is odd, the regular n-gon, so it has this thing basically like when it's odd, these 2 points have this point equidistant. Yeah. Yeah, and I guess I think if it's a question 1, I think you might need to show more working to prove stuff, especially when there are actually people making these mistakes. Like they're not proving. For example, like most people will think they just need to prove for points that they like, as opposed to all pairs of points, right?
Yeah.
Yeah, but the point is, any pair of points will kind of like if you line it up like this, there'll be like all these pairs that are witnessed by this point, you know. So, and basically any 2 points lie on a pair like this for some orientation of the circle. So it's balanced, and I guess it's obviously center free because every circumcircle is exactly this big circle. Every 3 points, the circumcircle of any 3 points is the circle itself. The center of the circle is in the center, which is not a point.
Yeah.
So it does not have a center. Okay. So this is both center free and balanced. So this is n odd works. And here is n odd done. Okay, I think I might pause it there because it might be a good kind of little process to try to figure out some other things. Yeah. Yeah, but you got n equals 4, yeah?
Yeah.
You got n equals 6. You get like triangles again.
Yeah. A is like you add like 2 points to the outside. Like one to the left of the top plane, and then one like extended on the right side. Like
It's not symmetric, you mean?
no, I didn't find it that way. Symmetric. Because the thing is, like when you add a point to the outside, one of the lengths is gonna be uh like like a bad length. So it's like because I don't know. It's hard to explain, but like you need to make like a big equilateral triangle for the other 2 points.
Big equilateral triangle. Oh, with what? What's the third point?
It's like you just add 2 extra points. Like one of the points is one already there, and the other 2 are complete equilateral triangle.
Yeah. So which point is it?
Yeah, any corner is fine.
Any corner, and then you like make a. Oh, you like make a point here.
Yeah, and then you need to
So whatever that length is.
yeah, that length won't like there won't be any points on the
It's crazy. What?
perpendicular. You should do. I think the other side is there, because like the equilateral triangle is downwards.
What?
The point, like, if you extend the right side of the triangle,
This side.
yeah, the one slot down, that,
Yeah.
Yeah.
Like the same length.
yeah.
And then what did you do?
And no, the point that was already there. Right?
Yeah. There.
Yeah.
Yeah.
No, it's that on the right,
That one.
Yeah.
One spot over.
Yeah, I think so. Wait. Wait a second.
Yeah. Well, that is an equilateral triangle. If that's what you're wondering.
Wait. What do you think it? But those 2 points don't have I don't think that works actually.
Oh.
Because those 2 points at the bottom don't have
Or like what about this point? This point?
yeah, that one has
Oh, it's actually me just drawing it bad. So that's meant to be perpendicular to that.
but the bottom 2 don't have one.
These two, yeah?
Yeah.
Oh, good. Yeah.
I didn't know how else so
Wait, does this work for 8? Let's see. We had like let me draw this. Oh, I should have drawn it then. Does this work for 8? That's what some other people said. 1,
1, 2, 3, 4.
Hmm.
Oh, that would. Yeah, I feel and that should work for any like theorem for anything.
Yeah.
Yeah.
Hmm. Why does that work though?
Mm.
So would the same idea work for the 6? Then like 6 would be like square. What if you did like this? Is that not doing anything?
Like the angles are off because those won't be straight lines.
Hmm. So just these 2 points, huh? Wait, is that obvious? So that doesn't work. Does it really work for n equals 12 as well? What am I trying to draw? A heptagon.
Yeah.
But these are already too far spaced apart.
Yeah.
Thanks.
Uh,
Does it work for this?
I mean, theoretically. Yeah. Well, okay.
Use of the word theoretically.
If you take 2 points in the same circle, it definitely works.
Yeah.
If you take like reflected points, they always work too, because you just end up with the mid 2 points. So you're only left with like the weird non-symmetric points. 1, 2, 3. Mm.
So like this one and that one. What's like the point?
The one at the bottom there.
This one.
Yeah.
Yeah. Is that like collinear, you think?
I think it's like
So you're saying this one is the one for these 2 points.
Yeah.
So the distance is like three little segments.
Yeah. I mean, that one's also 3 little segments. It's just,
On the other circle.
yeah, like it's split. Yeah. Um,
I mean, like this 2 segment thing plus that 1 segment thing is not equal to the 3 segment thing, right? Definitely longer.
well, that's not good. Maybe that one's the midpoint, the one on the top. I don't know.
Or the one on the top.
Yeah.
Hmm. Not actually that easy to prove, huh, for this. I mean,
You could bash it out with some like angle chasing intrigue if you really wanted to.
yeah.
There's still a lot of cases. Mm. Hmm. Wait, does the Pentagon one even work? The Pentagon one seems kind of.
Okay, so the pentagon one is like you need like this point with like a pentagon, so it works kind of that one with that point, right?
Where would the midpoint?
Yeah.
Oh,
Yeah.
that kind of.
Yeah, because that's exactly 1 chord.
Yeah. How about
And then it's the same on the other side.
what about like those are those angles the same? Like, is the angle outside the pentagon the same as the angle inside the pentagon? What is it?
Leftmost point and a point on the right circle one away from the intersections. Okay, leftmost point is this one. And a point on the right circle one away from the intersections. This one. Find the center point. Find the balance.
Does it exist? It's either the only possible one would be the one at the top. The top one next to the intersection.
That one.
Yeah. Which kind of makes a contradiction because like the one you're doing just then, the only possible one is the top one as well. Like they're different names.
Mm. Yeah. So this idea doesn't work, huh?
Apparently not. Who gave you the idea?
Huh?
Who gave you the idea?
Oh, these year sevens.
Oh. I mean, it wasn't a bad idea.
Yeah.
It was just one that didn't work.
Yeah, but the thing is, like when a year seven says the regular thing works, it's only that they thought of the regular. They only thought of the regular one, checked it for the pairs that are next to each other. That's what it means. So if it works, it doesn't mean they got it. Yeah, the triangle ones. Okay, let's have a look. I guess that's like a multiple of 3, right?
Yeah.
Maybe 12 can be done like that. Can 12 be done like that?
Aren't those like triangle numbers?
What?
Wait, then done like what?
Are they not multiples of 3?
Like adding more to like making a bigger triangle isn't like
Does making a bigger triangle not work?
well, it works for triangle numbers. That's kind of I'm pretty sure the bigger triangles don't even like pass that 2 case. Because like the bottom left point and the point right below the top point, like they don't really have them.
Huh. Hmm. What do you do? N equals 8. The triangles. Did you get 7 using another way?
7 is just like the hexagon.
With a center.
Yeah. But that doesn't work for the copy.
Triangles. So you have this triangle like this. Yeah.
Mm-hmm.
You have like this triangle like this. Does that work or not?
That would be 9.
Yeah.
I don't think you can do like the left point and like the one in the middle with the bottom.
Yeah.
And to the right.
This one.
No,
That one.
down. Yeah, down.
That one.
Oh, you can't do that one either.
Oh, it's a symmetric processor.
Yeah, and you can't do Like any of the 3 points in the middle.
What's the distance between this? That's the height of that triangle, isn't it?
Yeah.
Hmm. And this is the only way to do 4, right?
Well, for 3, the only way to do 3 is equilateral triangle.
Yeah.
So to do 4, since the 3 of the points still have to work, you're adding a 4th point to the equilateral triangle.
But the 3 points that already work may use.
Oh, they may use them. It seems like it would.
What's a Karen?
Karen.
Yeah.
It is. How do I explain it?
How bad is it?
Like as an insult.
Yeah.
Oh. I mean, it's usually used in it originated as a joke, so it's used as like in a joking context. So I mean, it's just saying someone's like the stereotypical like anti-vax flat earther. I want to speak to the manager type of woman.
Oh, really?
Yeah.
No, that's pretty funny.
Yeah, it's fun.
Yeah, like David's mom's name is Karen. And like,
oh boy.
I saw David today and he was just spamming like, my mom's such a Karen. My mom is such a Karen.
Yeah.
Yeah. Hmm.
Wait, just actually drank the whole thing from the side. Wow.
Cool. Messages, but always they're retracted.
Oh,
Yeah. I couldn't see them in time. I guess that's the point.
yeah. Roy just realized something didn't work or something.
Maybe I can show part B and focus us back on part A. It's kind of funny. It's ironic because it's like question 1A. Yeah. All right. So. Okay, so for part B, the question was for which n. So it seems like n equals even numbers is hard to even find balanced sets, right?
Mm-hmm.
So there might be a chance that you can't even find it if it's center free, you know? So I guess that's what I'm trying to prove. And so I guess the argument goes like this. Let n be even. You know?
Mm-hmm.
So the idea basically is like if you have 2 points, right? The balancing point has to lie on the perpendicular bisector, right?
Mm-hmm.
And you know, it could have another 2 points, right?
Yeah.
And basically because there's so many perpendicular bisectors, there's more pairs of points than points. There's lots of perpendicular bisectors. You're gonna have like sort of lots of perpendicular bisectors going to the same point, you know?
Yeah.
And so the basic idea is, you know, if the pair of points for which the perpendicular bisectors go through the same point,
Mm-hmm.
like it could be 4 points, right?
No.
Or it could be 3 points if they're the same point. Yeah.
Oh.
And so if it's 3 points, then that's the center. Yeah.
Yeah.
So how do I say this? So like, so if it's like this, right? Then this is the center of those 3 points, right?
Mm-hmm.
So basically, the idea is it can't be center free because there's too many perpendicular bisectors that have to go through that point, and two of them will have to share a point. Okay. All right. So
it doesn't work for any.
yeah. So if you have n choose 2 is n times n minus 1 on 2. Yeah? That's how many perpendicular bisectors there are. Yeah? AKA perpendicular bisectors. Okay. So if there's that many pairs of perpendicular bisectors, I mean, there's that many pair of points and that many perpendicular bisectors, then on average, each one of them, like each point, there's n points, right?
Yeah.
There's n points. On average, how many perpendicular bisectors pass through each point? Well, it's n on n minus 1 on 2 on n, right?
Yeah.
On average.
Yeah.
Okay. So this is equal to n minus 1 on 2. Yeah? So on average, n minus 1 on 2 pass through each point, right? But because n is even, right? This is a fraction, right? So so by the pigeonhole principle, there's going to be pigeonhole principle. There's going to be a point which is above the average, right?
Yeah.
They can't be on the average. So there's always a point above the average or below the average. Yeah. So there's gonna above the average is just n on 2. Yeah.
Yeah.
So n on 2 bisectors pass through some point, right?
Yeah.
Does that make sense?
Yeah.
Okay. Okay. So if you're a perpendicular bisector, you pass through that point, right? That point can't be involved in the pair of points for which the bisector is created. Yeah. Like, so like if you're at this point here and there's a perpendicular bisector passing, right? Like the 2 points for which it's the perpendicular bisector are not, it's not that point, right? So there's actually genuinely 3 points involved here. Yeah. So basically, the points which can be part of these perpendicular bisector things, right? So there's n minus 1 of them. Yeah. That makes sense? Because one of the points is, so the point, there's one point that's being passed through, right? So this point's got lots of perpendicular bisectors passing through. In fact, it's got n on 2 of them, yeah? Okay. But these perpendicular bisectors come from pairs of points, right? Right? And what pair, what points, where do the points come from to make these pairs? Well, they can come from any of the points except for that one, right? Like this can't contribute to that.
Oh, yeah.
Okay? So that means there's n minus 1 points from which, like there's a pool of n minus 1 points from which these perpendicular bisectors can come from.
Oh.
Yeah? And so, and the thing is, you don't want them to have any common points, right?
Yeah.
So basically, you need for every pair of points, there's n on 2 pairs, right? You need 2 different points, right?
Yeah.
Because if you have the same point, then it's got a center, yeah. But if you need 2 different points, then you need n points, right? But there's only n minus 1 point.
Oh.
So there has to be 2 perpendicular bisectors that come from 3 points instead of 4.
Oh,
which make it at this point the center of those 3 points.
Oh, okay.
Okay. So yeah. So actually, so that removes from our consideration the center free part. I guess to do the whole center free part, we really do need to be preparing for the problem for the lesson stuff. Okay. So that was Edwin's solution, yeah? Edwin's solution to part B. Yeah. So basically this proves n even cannot be done. And we already showed n odd can't be done. Yeah. Can be done. Yeah.
Yeah.
So that's part B. And I'm guessing part B would probably be worth like 4 out of 4. It'd be worth like 4. Maybe 4 points.
Oh.
4 or 5. I don't know. Then part A did seem a little bit harder than it first looked.
Yeah.
Yeah, if they don't share, there's not enough. If they do share, it's not center free. Yeah, that's what he said. Hmm. So I guess from this proof, if you have 8 points, right? You have 8 points, then you have like there's some point for which 4 perpendicular bisectors pass through. What about these 2 points? Is that these two? 1, 2, 3, 4, 5. Hmm. So I do suspect, for example, like why would it be like this in a test? It's almost like putting in a center, right, would make it easier to find a balanced set. Like psychologically, right?
Yeah.
Because why would it be another problem to find a center free?
Yeah.
You know what I mean? So maybe if you like introduced a center, it would make it easier.
Mm. That's it.
Hmm. Well, I mean, this proves that it has to be not center free, right? Whatever you come up with, yeah.
Oh yeah. So,
So,
at
for
least
example,
one center.
this is something's going to be like the center of something.
Yeah, that points the center of those three.
Which three?
One of the intersection points is the center of the 3 points next to it.
Yeah, so it's the center of like these 3 points, eh? And,
No, like the ones like right next to it.
oh, and the ones right next to it,
Yeah.
yeah. Wow. Yeah, so that actually does sort of help a little bit. So if it's impossible to find a center-free, even balanced set, then you must put the centers somewhere.
Yeah.
So if you're doing 4 points, see, like the 4th point is the center of the other 3 points.
Yeah.
You know? Obviously, one of the original 3 points can't be the center, right?
Yeah.
So once you put 3 points down, the 4th point has to be the center of the other 3.
Yeah. Ooh.
N-gon with center. It doesn't work with the triangle with the center. It's a regular hexagon. So Haibing made a comment. A regular hexagon. Draw a regular hexagon. Regular hexagon with the center in and 1 point removed. that work? It is an interesting observation. So that suggests a lot of things, doesn't it? The square doesn't quite work. Does it?
Squares are quite
This is the only way. Yeah, so the square doesn't work. Alright, does this work? How many pairs of points do we need to check? Oh yeah, because these are all equilateral triangles, right?
Yeah.
So then all the pairs of points here will work. You just need like a pair from here to there, right? So here to there. And this one to there and there, yeah? So they both give the center. Like
What if we remove 2 points as well?
2 points. What do you mean? Like another one here?
Yeah.
You keep removing them.
I mean, you could.
Oh, you mean like this point is not useful?
Yes.
It's not. It's not the
Not necessary.
Could you remove the other one too? Yeah, you could. That becomes the n equals 4 case.
Yeah.
Right. So 2n equals 4 is stuck together. Yeah. For some reason, gives an n equals how many?
6.
6.
But if you stick it there, it would make it an equal 7.
Yeah. So if you add that point, it also works, right?
Mm-hmm.
Do bigger hexagons. Bigger hexagons. Hmm. 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 Doesn't this work?
Do you have poetry? Wait, 1, 2, 3. Is it still without that?
I don't know. We can. We can even do it without another point, I guess. How many points did I just add? 6.
I mean, all the ones on the outside together just give you and then
Yeah.
the ones out inside to outside. It's like they're all equal.
Yeah, so the yes, it's the red and blue interactions. Yeah, so any interactions on the circle is fine, right? Because the center's there. But yeah, because if you were trying to do the octagon, the problem was the spokes, yeah.
Yes.
But these don't have problems with spokes because they're all equilateral triangles.
Yeah. I mean, you could just keep doing that. Just keep adding more and more points.
Yeah.
And so,
Oh, you don't even need to add them all.
you just need them so that they have an equilateral triangle together.
Yeah, like you don't even need to add them all.
You can add. That means you can add 2 at a time, which means that
Yeah.
all the equal. Yes.
Yes. Good old hexagon. It made us think outside the box.
Yes.
Yeah, I think this is somehow it, right? So it's like a meta solve, like all good
Yes.
exam problems. So basically, we know that it cannot be done when there's no center. So we just like maximally center it.
Yes.
So we have a circle, right? Yeah. And put it in the middle. Make sure there's a center.
Yes.
And I think you can just like
You should start with
do an equilateral triangle.
I think you need the n equals 4 first. You can start with 3 because
Can't you just add it whenever you want?
but if you add 2 at a time there, they'll all be odd, which is kind of useful. Like,
Oh,
yeah. So you just start with 3 and then you add 2 at a time, which gives you
start with 3, like here.
yeah, like the n equals 4, and then you add 2 at a time wherever you want. Because yeah, that gives you the whole thing.
That's 4, yeah?
Yeah.
So what are the rules here? The rules, we can add wherever we want.
As long as the distance between 2 points equals like the radius.
Yeah.
Yeah.
So we start here, yeah? Start there.
And
So then, yeah. Yeah, it's kind of funny, like if you think about it, right? If you're presenting this stuff to like little kids or people who don't know maths,
yeah.
it's like you just get stuck, you look stupid, right? And then they hate you.
Yes.
Right? But the alternative, think about the alternative, okay?
You already finished the problem.
You just fake solve it,
Oh.
don't mention it, and then they love you. It's like, was IMO question really that easy? It must have been.
Whoa. Easy.
Alright, let's see what happens. So I use another color now. So I can basically add it anywhere.
Yeah.
Is that really that sick?
Yeah, you can. Yeah.
Are you kidding me? So I can be like,
Yeah, you really want
what are you saying?
to.
Saying I don't really want to?
Well, I mean,
Yeah, so this is not a cross. It's gonna meet here.
yeah.
So the point is that this arc
That's
length has to equal this arc length, has to equal the radius. Yeah?
the direct distance is the rate.
Yeah.
Yeah. It looks really wonky, but that's fine.
Yeah, so with your idea, I basically tried the octagon. Yeah. Ninagon or whatever. Yeah. I guess the point is all the things on the circle are actually easy to pair up, yeah? It's just when you do the center with one of these, it goes off, yeah?
Yeah.
And so you just make them into equilateral triangles, yeah?
Yeah.
And I guess the fact you can remove one point, it can kind of make you think that you can remove any point.
Mm.
Yeah. Yeah. This is the Haping idea. Okay, so does that actually work?
Well, yes. uh,
Yeah, because you're never worried about the pair on the circles.
yeah.
So every pair you're worried about. So any pair on the circles, the center is the thing. That's pretty sick, huh?
Mhm.
But then you're worried about the center paired with one of the circumference points. And so all you need is the equilateral triangle to do that.
Yeah.
And it doesn't introduce any more problem because the point there solves it. Yeah. Oh,
No.
yeah,
Mm.
there you go.
Well,
Basically, yeah, I think it was just like a whole lot of don't trust year sevens. That's one of the moral of the story. Don't trust year sevens.
Yeah.
All the ideas were fake solves.
Just keep it in your thought.
Mm.
Yes.
It was also funny that like so that one of the year seven ideas was you do two pentagons, right? So therefore two times anything works.
Okay.
Yeah. And the thing is like I don't think they even realize it doesn't even get all the even numbers. Like
Both of you.
because you realize it only gets multiples of four, right?
Yeah. Maybe like odd beacons. Odd beacons.
Yeah.
Yeah.
Oh, Crystal, hello.
Tuesday? What? Wait, 47.
Everyone so far has told me they're doing an assignment while watching. Sean's doing an assignment. Having's doing an assignment. Edwin's, I think, doing an assignment while not watching. Are you doing an assignment?
Oh, I think she's doing the STD assignment.
Okay. Oh, there you go. So actually, it would have. It seems like it's easier to do this knowing part B, right? Because if you didn't know, you couldn't use a center. You might be trying to many possibilities, yeah.
Yeah.
You can name this the hyping point. Okay, let's present some fake souls. So this is 2017. Question 5. Okay, so I really like this question. I kind of like this question just because, like, let me understand like what kind of questions. So it kind of gives me an idea what kind of questions make it to the IMO. Yeah. So some questions are not necessarily. Some questions can be hard in like very different ways, right? Like this question, I feel like it's hard in the sense that you could potentially fake solve it in many different ways.
Yes, and not even.
Yeah. So like, so for example,
like this is the algorithm.
Yeah, let me just explain the problem and then I'll tell you what we got up to last time. Yeah. So basically, the problem is you have n times n plus 1 people, right?
This.
Of different heights, but they might as well just be numbers, yeah. Okay. And you want to remove n times n minus 1 of them, yeah. And so the ones who are left, right? The people who are left, there's 2n people left, yeah. Yeah. And they have to have the property that with the new height ranking, so the people who are removed, we don't count them anymore. That the tallest two are next to each other, so there's like they're paired up next to each other.
Yeah.
You know, so they're adjacent, or there could be a gap apart where someone's been removed, right? And then the next two are next to each other, and all the way down there's n pairs, right? So there's the shortest two. Yeah. They're saying about the primary school, like no one cheer disappointed, no one challenging. Oh, let me tell you, actually, there was one kid, he must be like entitled or something. He said to me, he said, can I do the next 2 hours, I've done it for 2 hours.
Yeah.
Can I do the last 2 hours next week? I'm like, are you
The
kidding me?
next 2 hours of the lesson.
Yeah, and then like the test, AIMO.
Oh,
It's like, are you kidding me? You think you can do it for 2 hours and then resume?
Wait a week.
You take it like adjournment. I need to call a recess. Like not just like have to go to the toilet, right? It's like I need a week's break. I need a week's break before I can continue this exam. And I'm like, well, you must have a fantastic reason for this request. This fantastic request. What is it? And he's like, oh, I'm tired. Just tired.
I'm fine.
I
I'm fine.
was like, yeah, I mean, if you think not being tired is a human right, then I'm a tyrant. Because I said no.
No.
So this kid is going places.
Yeah.
Yeah.
How old was he?
Huh?
How old was he?
Year 6.
Oh.
Which is like, I've been telling people, like, it's a long exam,
Yeah.
Okay, so the first part we did last time. So my strategy for all these problems are basically just do n equals. So they said n equals 2, but my strategy for all these problems is do n equals whatever the cases are until I get something. Okay. Yeah. So last week what we had was this. I didn't present the fake solve. I actually acknowledged that this is a fake solve. Yeah.
Oh.
It's not my fake solve. It's just this is a potential fake solve. Yeah. So when n equals 2, okay, there's always, so the tallest, so if we call them 1, 2, 3, 4, 5, 6, right? Like that's who they are. You just only care about their heights. And out of the 4, 5, and 6, there's 2 of them within 1, right?
2 within 1.
Mm-hmm.
2 pairs that are within 1.
Yeah, so like either 4 and 5 are 1 apart, or 5 and 6 are 1 apart, or 4 and 6 are 1 apart. Like they could be next to each other too. It's just they can't be all 2 apart. Because you like put 4 here, 5 here, and then there's no way to put the 6. Yeah. Okay. So I think this question should be called a study in fake solves.
Yeah.
Okay.
Wait, is this the fake solve or is this the real solve?
Well, the thing is, one thing that was kind of interesting was the fake solves were universal. So in a sense, they had to contribute to the solution. It's just that they weren't the end step.
They weren't actually the solution.
Okay, so yeah, so hopefully that's raised your level of alertness. Okay, so for example, you have like a 4 and a 6, right?
Mm-hmm.
And so the plan is what you do is you need to remove 2, yeah?
Mm-hmm.
So n times, so this is n times n plus 1 is 6. And you need to remove n times, you remove 2, yeah?
Mm-hmm.
Okay. So you remove this one, right? Because that's getting in your way.
Okay.
Because your 5 is like here, Your 5 is here.
Sure.
Yeah. So you basically have to remove that one, right? Because you can only remove 2, yeah?
Uh-huh.
Okay, so first of all, like when it's 3 things, right? In the top 3.
Yeah.
And like these are 2 are like 2 apart, right?
Yeah.
You basically like if there was like a 6 and a 4 that was 2 apart. If you wanted to keep them, you have to remove the ones in between them, yeah? Sorry, a 6 and a 5. If it was 6 and a 5, 2 apart. So here, a 6 and a 5 are 4 apart, yeah? If you wanted to keep them both, right?
Yeah.
You have to remove 4 things in the middle, which you can't do, right? So if 6 and 5 are far apart, you have to remove one of them, yeah?
Yeah.
So, but if you remove the 5, so if you remove the 6, you're kind of stuffed, right? Because you can't remove the 2 in between the 4 and 5.
Yeah.
So you have to remove the 5, yeah?
Uh-huh.
Yeah. So I guess part of this is kind of just seeing how to do stuff, and also, I think last time I made it more case bashy. So actually, you're more tempted with the fake solve the longer it takes you to find it, because you think that's how long the problem was, right? Okay. Okay, so then you kill the 5. You have to, basically, right?
Yeah.
And so now it's the top 2, and these are the bottom 2. Yeah, that makes sense.
Yeah.
So we move on to n equals 3.
Wait, so you just do that for everything. Like out of the top 3, you find the 2 that are at least 1 apart,
Yeah,
and then you take out the one between the 2 that are 1 apart.
Yeah.
And you take out the third one.
yeah.
And what do you do if they're all 3 together?
Oh, if they're together, you get a free move, so it's easier.
It doesn't matter. You can take out any 3 of
Yeah,
them.
like if the 5 is here, you just get to choose one now, right?
Okay.
All right.
Looks good enough for me.
Yeah, fake solve number 1.
Yeah. Great. This is just how many fake souls you can convince me of working.
Yeah.
Oh no.
Okay, so n equals 3 was just there to symbolize getting through it, getting it through.
Oh, no.
Okay, so there's this case where, the 4 and the 6 could be here, right?
Yeah.
And the 5 is here, for example, right?
Oh, that doesn't work.
Okay.
Oh my goodness.
Yeah.
Well.
Yes. Okay. So
Oh, then you can just use 4 and 5.
yeah, you can use 4 and 5, yeah? So it's actually saved. So you
For
use
now.
for now, yeah. So if that happens, you use 4 and 5. And get rid of the 6. Yeah? Okay, so for that, you have to show that basically they'll be close to the ends, right?
Yeah.
Yeah. Yeah. So I guess it depends on how far you go. How far do you go? Yeah, so then you go n equals 3, right? So this is stuff we did on Monday, okay? So I'm just reminding you so that I bet you no one watched it and then no one remembered it.
Yes.
Yeah. It was after 9 as well, so that is a pretty possible. So n equals 3, now you have 12 spots, right?
Yeah.
5, 6, 7, 8, 9, 10, 11, 12.
Yeah.
Okay.
Yeah.
So let's proceed by induction, yeah?
Oh.
So there's now going to be out of the 4, 5, 6, it's not 4, 5, 6 anymore, it's now 9, 10, 11, 12. Yeah? There's 2 that are 2 apart.
So are you gonna take n plus 1 with them at the end? Like n plus 1.
Yeah, so you kind of it's like you have 9, 10, 11, and it can't fit, right? So it's 12. Yeah?
Yeah.
Then you kill these guys. Alright?
Sure. Sure. And then you kill the ones in between.
Kill the ones in between. And see, the good thing about it is in some sense you're forced to do that, right? Because you can't let them. So you basically have two choices. They're both very extreme. You have to kill all of them,
Yeah.
right? Or you have to kill like gaps between some of them.
Yeah.
And they're both extreme because there could be a lot of gaps, right? So,
Yes.
so even if you had to kill the gaps between them, you had to kill the other two, right? So you're killing four things no matter what, and you basically have to do it. So if you think about it, like if your argument is going to be some kind of generic argument, right, that has to work for all the cases, then the fact that there are these weird cases mean that the argument has to respond like that, right?
Yeah.
Yeah, and so notice Singh said in the chat, now you're left with the n equals 2 case, right?
Whoa.
Yeah.
That's
Isn't that cool?
crazy.
Because now you got that paired up, right? So you need, how many do you need to remove? You need to remove 2 times 1, 3 times 2, right? Yeah.
Yeah.
And you remove 4. You got 2 more left to remove, yeah? And then you have this pair already, right? So there's only 6 spots.
How is the number you choose like expressed in terms of n? Like how many?
Oh, how many of the top ones?
Yeah.
Oh, it's just equal to n plus 1.
N plus 1. So n times n plus 1 minus n plus 1 minus.
Yeah, okay. If you want to do that, yeah. So it's n. So it's n times n plus 1 altogether, right?
Yeah.
You're removing n plus 1, yeah?
Yeah.
Okay.
I'm not sure.
So that will leave you with n minus. But you also have 2 things that are good as well, right? So you can maybe remove like another 2, yeah?
Yeah.
So it's n minus.
Wait. That easy is n squared minus 3. It's meant to be n times n minus
N squared minus 3. Oh, hold on. So this number, yeah, n plus 1, yeah.
20 of them. So if it was n equals 4, there are 20 numbers. Would you remove 5 of them?
So there's 5, yeah. So there'll be 2 that are 3 apart, and you remove the other 3, yeah. You're moving 5, yeah.
So you're at 5, you're up to 15. 2 of them are like next to like the ones you already used. So you still have 13.
Yeah.
What happened to the other number? I only have 12.
So you have 20, right?
Yeah.
You remove like 3 in between 2 of them, and another 2, another 3, yeah.
Oh, and
So you move 6.
no, that's not good. That's one.
Oh, so it must be. So this number here is. So this number here is n plus
yeah.
1. This number here is n minus 1. N minus 1. So you're removing yeah, you're removing n minus 1. Yeah.
Yeah. Which would be minus 2n, which is, yeah, that's the right number.
Is it?
Yeah, because the plus 1 minus 1 cancels, and it's n times n plus 1 minus 2 then. It is n times n
Minus 1. And then, wait, should this also be n minus 1?
minus 2. No, like, no.
Oh, yeah, you're removing them anyway, right? Yeah. Yeah, you don't keep these 2. You kill them all, yeah? As far as you're concerned. Yeah?
Yeah.
Alright, so it's minus 2n. 2n.
no.
minus 2n, yeah?
Yeah, it's that minus 2.
So that's n times n minus 1, yeah?
Yes.
What just happened?
Wait, that is bad. The middle line. No, you're that thing's n squared plus n minus 2.
I never even did it. I'm just trying to get the answer.
Yeah.
Okay, so
N squared plus n minus 2. Which is that?
okay. N squared minus n, yeah?
Yeah.
Which is how many which is actually it should be n minus 1 times n, right? That's what the lower case is, yeah?
Yeah.
And how many more do you get to remove? Well, you know, you've removed that many, right?
Mm-hmm.
So it's n times n minus 1 minus 2n, yeah? Is that right? Yeah, so it's n squared minus 3n, yeah? Oh, I should have just factorized it, but it's n times n minus 3, which is the n minus 1. It, like, wait.
Wait, no.
It should be n minus.
It's minusing like n minus 1 plus 1 minus n minus 1 minus 1. So like for the case below that it would be
You're removing n minus 1 times n minus 2, all right?
yeah, that's how many you should be left with, right?
You should be left with 2n minus 1, right? Right, so you're removing, so you have n times n plus 1, right?
Yeah.
And you're removing n times n minus 1, yeah?
Are you removing 2n?
No, you're left with 2n. Because you have the 2n, you have the n conditions, remember?
What?
See, here we're removing, because and when n equals 3, right? You're removing 6.
What? And
Oh, sorry, okay, so that is 2n. But when n equals 2, you're removing 2. Yeah?
are you removing?
6 remove 2, yeah?
Oh, for just that thing.
Yeah, so you're removing
Yeah.
you're removing n. Oh, wait a sec. Yeah, so you're removing n times n minus 1, yeah?
Yeah.
But now you want to be removing n minus 1 times n minus 2, right?
Oh, I was just thinking like the other way.
Oh, okay.
Wait, so for the second step,
Yeah.
so after you've gotten, so it's n times n plus 1, and you've removed 2n of them. So now you're left with n minus 1 times n. Right?
Now you're left with n minus 1 times n.
No, like that's
Yeah,
the smaller
yeah.
piece. Yeah.
Yeah. So that's how many spaces are left, right? And now
Yeah,
I want
and
to
then
figure
you can do,
I want to figure out how many more I can remove.
isn't it just the same as
These two numbers.
like those two numbers minus 1.
Minus 2.
Yeah,
Plus
minus
2.
1.
Yeah, so it's these numbers, but you have to have the 11 and 12 back, yeah? Because you never actually deleted them. You just didn't count them anymore, yeah? Like, you know what I mean? Like, there's a difference between deleting stuff and not worrying about them, yeah? So it should be minus 2n plus 2, yeah? So it should be n and n plus 1 minus 2n plus 2. Alright. It's n squared minus n plus 2. Is that right? And then that is n minus 1 times n minus 2, right? Yeah.
Wait, what? That's also bad.
Oh, that's not right. Wait, I did something wrong.
I think like the better way to do it is like, so you ignore like the 11 and 12.
Oh wait, yeah. Okay, hold on. So I'm trying to. How many am I meant to remove? It's n times n minus 1, not n times n plus 1. Yeah, so it's n times. Did I do that? Did I write n minus 1 as well? It's n times n minus 1
Yeah.
minus 2n plus 2. Yeah? Because that's how many we went to remove.
Yeah.
And that's how many we've already removed.
Yeah.
And so now it should work. Because now it's n squared minus 3n plus 2. Yeah?
Yeah.
Minus 2. Minus 1. Okay? So that works.
Oh.
Okay. Yeah, so can you see that each case reduces the previous case, right?
Yeah. Yeah, like that. Yeah.
Yeah. And then you're done by induction.
Ah. Okay.
Yeah?
Yeah.
Yeah. Fake solve number 2.
Oh no. Ah. Why does that not work? What?
Yeah, it's kind of cool, but like, I mean, yeah,
Oh,
if I just present this and then say it's a real solve and no one noticed a fake solve until later, and then you're just like, no, it's because you're dumb. You just didn't get it. Yeah, and then it's over and everyone's happy, right?
Wait, what if the middle two are 2 together? Does that still have the same?
Yeah, so the problem is if you have like 11 and 12 isn't here, right? If 11 and 12 isn't there, but 12 is here, right? Yeah.
Yeah, and then you need extra crosses. Yeah, it's this one. Oh.
Yeah, you see? So basically, you have two options here. You can try to strengthen the induction hypothesis, or you can come up with a new idea, yeah? But actually, this induction actually must have, like, though it doesn't work, it must actually be universal, I think. Because in some sense, you do have to remove those things, right?
Yeah.
You can't get away from removing them. It's just that, yeah, you might have to do it in a different order, yeah?
Yeah.
Yeah, so fake solve number 2. Okay. Yeah, but as you're doing it, actually, I think as you're doing it,
What's the difference with fake solve number 1?
it's actually the same.
Oh.
It's just this one you carried it all the way out to the end, so you think you've done a lot, right? Because we even decided how to match up the ends and all that stuff.
Oh, so that's like the full version.
Yeah, the full. This is the complete version of the fake solve. Yeah.
Yeah.
But it's not a complete waste of time because you do realize it's an induction step. Yeah.
Yeah.
Okay, it's just probably not how it's done. Okay. But if you haven't done a problem like this before, like I really haven't done many of these problems, I'm thinking like, oh, like how hard could the problem, like, could I have to strengthen the hypothesis? Do I have to do this? Is it possible? Like all those questions, like you have to answer them. You know what I mean?
No.
If you do more questions, like you'll be like, oh, they don't come up very often, so maybe I can try to ignore them. But like purely mathematically, like the questions all exist, you know, and so it can be a bit of a headache. Yeah, so that's like the full-blown version of the fake solve. And
No.
yeah, I think I've shown some people this and they never said anything, and so I was like, all right.
All right.
I even suspected James actually stopped here because of his face.
He what?
I think he might have done this.
Oh.
Yeah, so
he did this in the actual exam.
I don't know what he did in the exam. It's possible.
But did he agree with you when he presented it?
I never presented it.
Oh, you did.
Yeah.
Oh.
So I never claimed it was true. I just kind of sketched some stuff. And then like,
You didn't question it.
no, he thought about it himself. He didn't go off me.
Mm.
So it's very tempting, especially like imagine if you took a long time to figure out that it was an induction, right?
Yeah.
Because that's not that easy to figure out. You know what I mean?
Yeah.
Because like you have to actually phrase this statement in the right way. You know?
Mhm.
So then the next one like is the top 5 or within 3 of each other. You know? And then those numbers work out exactly right. That's what this was the realization of. Yeah.
Oh.
Okay. Yeah. So no, don't be too discouraged with the fake solve. I mean, the point is the fact that it exists. It means like the other people are fake solving and stopping, and you can keep going, right? And the fake solve contributes to the solution. Yeah. So these are all pretty good observations. So then, okay. So what do? Maybe you can actually clean up this idea a bit. Okay.
Okay.
So you can clean up this idea a bit. So, for example, here, should I give people some more time to think about it? People interested in thinking about it?
Mm.
Yeah, I think it'd be more interesting if people thought about it a little bit. Okay, and it might be interesting to try to like. Sometimes, like when people feel uncomfortable, like when you start a problem from the start, right? You kind of feel comfortable with it. But if you start in the middle, sometimes it feels uncomfortable. So maybe this is a good chance for you to experience what it's like to start a problem from the middle.
Oh.
Okay.
Okay.
Save it like you did it. Could you save it like you did it with fake solve 1? Oh, okay. So I think. Oh, that's a good question. So can you try to save this with like a save fake solve 1, right? So I guess the answer is
How did you say? Oh,
by doing a choice. Yeah.
Mhm.
So in this case, I guess. So fundamentally, you can't get it on the side, right? That's something you can't do. Okay. But you can try to save it, like so, and I don't think you can save the argument in a very easy way for like n, yeah, because that's basically solving the problem. But I do think you can save like n equals 3, for example, kind of like yeah. So there's some ways you could try to save it, like you could try to be like, well, I haven't used up all my choices, right? So I don't just like see, it's not just the top 4 that works, right? It's also the bottom 4. So if the top 4 doesn't work, right, then the middle is kind of taken up by the top 4. So there's more spaces on the outside for the bottom 4, right? You know what I'm saying?
Yes.
And so if it doesn't work for the bottom 4, then the bottom 4 and the top 4 are all in the middle, which is very, very crowded now. Yeah, or they're like spaced apart, like in this way. So I think there are some ways to try to save it with cases. But you'll find it's kind of it's a good question. So, and you keep looking. Yeah, so I guess how you might save it is kind of like, well, you might think what condition you need and what you can get from the n equals 2 case. Okay, so that's what I'm going to go over next, but I want people to kind of think about it a little bit more, hopefully. And so this is fake solve 1 and 2, okay? But it's also progress in the problem. So it's not that you have to begin from the beginning, right? Like basically like you have an intimate understanding of the problem. Like you can kind of also gauge how much you've understood the problem, because if you think about this problem for n equals 2, right?
Mm-hmm.
Like there's what, like 720 permutations or whatever.
Yeah.
And you have to bash all the cases out, right?
Mm-hmm.
And when you realize it's about 2 of the top being close together, that's actually cutting out to orbit basically 2 cases, right?
Yeah.
So that's huge progress. Okay. Even though like the first part is huge progress with a tempting flaw, like tempting sort of way to fail.
Yes.
And then here you basically covered like so many cases out of the potentially like infinite cases.
Yeah.
Okay, so it's not nothing. And you keep going. Yeah. So in the AI mode practice test, this was question 9, right? N equals 2 and n equals 3. That was question 9.
Yeah. Oh. Wait, that would have been super hard stuff. It's like, there's still so many cases without
Yeah, but you could have done the first part.
yeah, my bad.
Okay, so let's take a bit of a, well, not a break maybe for me, but like I could keep going too. But the point is, you want to think about what's going on before we keep going. You know.
Yeah.
Yeah, I might keep going because it's hard to really simulate question solving time, especially for long time questions. Okay, so we just did fake solve 1 and 2, and now we're trying to keep going, yeah?
To get fake solve 3.
So like, and one thing that was kind of annoying about this condition, right, is like this thing is kind of a bit, you don't know where they are, right? And so if you say it like that, they end up in the middle without you knowing, right? So it might be nice to come up with another way to state it where like you really know where the edges are, right? So the point is like you have these two, right? If they're kind of within, if they're anywhere in these three, then you can cut off the side, right? And you're done. So another way of saying it is you can partition it into 2 blocks of 3, right? Yeah. And then you can say instead of these two are within within one of each other, right? You can say that there'll be 2 of those on one of the sides, you know? So now it's like actual pigeonhole principle. Yeah. So 2 of 4, 5, 6, yeah, on either side. Yeah. And there's 2 here, yeah? Yeah. Okay, because there's 2 sides, there's 3 things, yeah? Okay. So that way, so you can already see that addresses this case, right?
Yeah.
You don't have to deal with the choice of 4, 6, or 5, 4 based on them being on the side. Yeah? This automatically has these 2 on the side. You see that?
Yeah.
So then you just pick those 2. You pick these 2 the first time. You don't have to adjust. So now it's just one case. So that's definitely something, right? Okay, and what it is, we'll have to see. Okay, so this might come under the choice of trying to strengthen the induction hypothesis. Yeah. So here, if you go to the next case, it'll be okay, 3 groups. You know, and the nice thing is there's 3 things, and there's 2 groups of 3, yeah? There's 4 things, there's 3 groups of 4. See, because it's n times n plus 1, so it's always n plus 1, and there's n of them. Yeah, it's always worked out like that. Yeah. Okay. So here, by the pigeonhole principle, there's 3 holes and there's 4 things, right?
Mm-hmm.
So there are going to be 2 of them.
The middle holes.
Huh?
Like if 2 of them are not in the middle.
Oh, okay. So you know what happens on the side. We do the induction, right? Then you're worried about what happens in the middle, yeah? And you have like 11, 12, yeah? So you're worried that now that it's in the middle, yeah? Okay. So if we try to strengthen the induction hypothesis, then the one natural thing to kind of see is, so what's the problem with it in the middle, right? So what happens is when you do it in the middle, right? See, and this probably leads to this idea a little bit as well, because now you're doing the n equals 2 case, right? With like a barrier in the middle. Does that make sense?
Oh yeah.
They have to be these two can't be next to each other basically. That's like the main problem, yeah. So that's the barrier is a very natural thing to see in that respect, right? So it's not the same as doing the n equals 2 case anymore. It's n equals 2 with a barrier, right? Okay. So what does that mean? So maybe we can try to come up with a statement that strengthens the hypothesis, yeah? So what if I say, okay, not only can I do it for n equals 2, I can do it in such a way that I always remove one thing from each side. Yeah? So can you see in this case, I removed the 4 and the 6 this thing from here, and the 5 I removed there, yeah? If the 4, 5, and 6 were all on the same side, I would just pick one of them and then pick a random one here again. Right? So I can actually say that I will always remove one from each side, right? Okay. That makes sense?
Yeah.
So look at it now. So now when I have when it's on the edge, I'm done because I know what to do on the edge, right?
Yeah.
But when it's in the middle, okay, I have the induction hypothesis to help me now because I can remove one from each side. Yeah? Yeah, does that make sense?
Yeah.
So because there's one on each side, right? And the thing is there can't be 2 on that side because if there's 2 you just do the sides, right?
Yeah.
Yeah?
Yeah.
So then there has to be 1 each, right? So then there's 3 and 3, yeah? You remove 1 from each, right? Yeah? And then the overall result is you have 3 parts with 2 from each, right? That makes sense?
Yeah.
So not only do you have the stronger hypothesis.
Wait, what happens when it's a 2 2 0?
Oh, give me a sec. What's going on? Oh, I hate this freaking QuickTime.
Yeah.
Okay, so what are we at here? So we're saying that we have a barrier, right? So the point is, if you remove from the middle, there's a barrier in the 3, right? Which is natural to make a barrier in the 6 places, and then you can actually see that by the pigeonhole principle, there'll be 2 on one of the sides, And not only that, you're actually able to always do it to remove one from each side. Yeah. And so if you remove one from each side, and you remove two in the middle, and there's one from each side, then you remove two from all three spaces in the next one up. Right?
So if you have the 2 to 0 case,
What's 2 to 0? Like 2 here, 2 here,
yeah,
and nothing here, yeah.
you just do the side case, but then like it's reverted back to the outer value because then you would have a 2 and 4 on that.
Oh yeah, so if you have 2 to 0, you try to do side case, yeah?
Yeah, and then that will remove the barrier.
Yeah, that would remove the barrier. Yeah. Okay, are you ready?
For fake solve.
Yeah. That's called fake solve 3. Proofs are hard.
Yes.
Okay, so why is that fake solve 3?
Good question.
Why is it fake solve number 3? Yeah, maybe this is more interesting than solving the problem. Just trying to figure out why these don't solve the problem. So I'm pretty sure, like, once I've solved it, I looked up the solution. I'm trying to look up the solution. I can't. Basically, I can't understand what anyone else is saying. And the ones I do understand are fake solves. So I couldn't like check it or anything, but. And they're all a little bit too short to be like, they're all a bit sus, you know?
Yeah.
Just do the following algorithm. And there's like 2 lines.
Yeah,
no. Yeah, you can tell like the complexity of the problem involves these concepts universally, so they can't avoid like those kind of things too easily. Let's just say that. Okay, so why is it a fake solve?
I don't know.
Okay, so the point is we strengthen the induction hypothesis, right?
Yeah.
And so then we prove the strengthened conclusion, right?
Yeah.
Yeah. But not in all cases. Yeah.
Ah.
So now the point is the strengthened induction hypothesis gives you the strengthened conclusion if this is like 1, 2, 1, right?
Yeah.
But when it is on the sides, you don't get the strengthened induction step anymore,
Yes,
right?
that was why I was a bit sus.
Yeah.
Because the barrier disappears.
You were onto it.
Yeah.
No one's trying to get you away from it.
I thought like you could just do the strengthened one and the weak one at the same time.
Yeah.
So if it's like this, then you just use the other one.
Yeah. So there's no way to do it now because you can only remove 1 from that, right?
Yeah.
You have to remove 2 to complete the strengthened thing, right?
Yeah.
So it's not strong enough. Yeah, like the induction hypothesis can be strengthened, but the induction step also needs to be strengthened.
Yeah.
And it's not strong enough. Okay?
Not
good enough. But hey, there's been lots of progress, yeah? Actually, it can be fixed, I think. See, the idea before with the lower cases, right? The lower numbers. See, what has to go here now? It has to be like 1 and 2, right? Yeah. So, 1 to 9, 12. Like you basically know where everything goes, kind of thing.
Yeah.
And you do kind of discover it's like you have to remove them in blocks like this. You don't really have a choice. This has to be basically right, but it's not at the right time. Yeah. Because how do you deal with 12, like 11, 9, you know what I mean? 10, 9, 12, 11. How do you deal with that, right?
Yeah.
You have to either remove all of them or you have to, right? See, if you remove all of them, you have a big problem because you're not guaranteed for the other things to be in the right order too, right?
Mm.
So if you remove all of them, then you're forced to use some of the others.
Yeah.
That's the problem, yeah?
Yeah.
Whereas if you only remove sort of what you need, you're not at the mercy of the next step, you know?
Yeah.
Yeah. So in some sense, it's almost like it's almost like you have to remove it like this.
Yeah.
It's just it might not be like what you think it is. Like it could be like 1, 2, and then you're removing the 9 and 12, right?
Mm.
You know what I'm saying?
Yeah.
Or it could be the middle ones and the 1, 2s on the side. Yeah. Yeah. So strengthening the induction hypothesis this way was very hard, and you might be tempted to try to. So basically, what the idea is like, okay, it might end up in the middle, right?
Yeah.
Let's try to deal with it. Yeah.
Yeah.
Okay, but then you kind of discover it's pretty hard to deal with it in the middle. Yeah.
Mm-hmm.
So you might just scrape through here, with like, but then you lose your hypothesis again, almost. Yeah. You might just be able to get through it if you consider all the cases. It still might. It should be true. So you should be able to prove it. Okay. But it's kind of hard, and if you have to consider cases separately, then the argument is going to be hard to generalize as well. Yeah. So depending on how stubborn you are, you may choose to. Yeah, you can choose to do the Yeah, I was kind of doing both ends at the same time actually. You didn't really need to. So you can choose the other option is also possible. There's one very kind of not obvious. I don't know if it's how obvious it is, but it's pretty obvious, right? Like it might end up in the middle. Okay. Well, what if I focus on the ends? Yeah.
Yeah.
What if I focus on the ends? So why is it ending up in the middle? Well, because I'm focusing on the top 4, right?
Yeah.
Yeah. I also have the bottom 4. I also have the middle 4. Yeah.
Yes.
So if I focus on the top 4, it might end up in the middle. Yeah.
Mm-hmm.
If I focus on the bottom 4, it might also end up in the middle.
Oh, but in the middle.
And the middle 4 cannot end up in the middle, right?
Yeah.
Yeah. And another way to think about it that is like, well, why don't I just see what ends up in the ends? Yeah.
Yeah.
So this is actually kind of nice because it actually highlights the sort of the relationships between the numbers. So there's actually also another pigeonhole principle, right?
Mm-hmm.
Pigeonhole principle fest.
PHP.
So there's another pigeonhole principle that says there must be a repeat in the block. Yeah, kind of obvious.
Yes.
Yeah, so there's 3 types of things. So you can even call these like top. So it's like top times 4, mid times 4, right? Bottom times 4.
Bot.
Yeah, bottom. Right. The bot times 4, yeah? But there's only 3 things in 4 spots, so 2 of them have to repeat, right?
Yeah.
And you might as well assume it's the middle ones, because if it's the top and the bottom ones, then you're done, right?
Yeah.
Right?
Yeah.
So then what happens if the middle ones end up on the sides, yeah?
Mm-hmm.
So the middle one end up on the sides. So I have middle, middle, same middle, middle, yeah?
Yeah.
So kill these 2, yeah? You have to, yeah? You basically have to. You kill them, yeah?
Yeah.
Okay. Yeah, so can you see what happens now? You have the middle ones, and then you have just like 1, 2, 3. Well, it's still the right number of spaces. We made that observation before, right? Yeah. Yeah. So basically, and there's the top ones are going to come, like these two are going to have repeats as well, right? So this could repeat the bottom two, for example. So this is not repeating the bottom two, right? So all the top two. That's kind of crazy. Actually, maybe it's more realistic if that happens, yeah? Just middles on the sides, yeah? Because otherwise there may be tops being repeated. Yeah. And see, then where does the tops and bottom go? So there has to be like a top, bottom, right? Top, bottom, yeah? Okay, and then it's top, top, bottom, bottom. See how that works? Yeah. So it's actually not that bad to remove the middle, right? Because look at that, you just keep top, top, bottom, bottom. Well, in this case, I guess, you keep bottom, bottom here, and then top, top, right? Yeah. Solve it.
Exo number 4.
Yeah.
Yeah.
Exo 4.
Yeah.
It's on to the meta game. Yeah. I mean, this is not attempting fake solve, because when you're at this stage, you're like, well, I'm pretty aware of the issues in this problem. Yeah, or you're kind of aware that it exists traps. So you're not going to settle for this one that easy. Right? Yeah. So that actually does work for n equals 3. Yeah? That's the problem. Yeah. That's the temptation, right? So it's when it's n equals 4. Yeah, so I'm going to just draw the n ones. And there's 4 blocks, yeah? Yeah. Yeah, so now there's not a middle anymore, right? It's top. There's 4 groups, yeah? You know what I'm saying? 4 groups. So 1, 2, 3, 4. And there's 5 lots of each, yeah? Okay, it still kind of works. It's like the 2 and the 3 are the middle groups, yeah? Yeah. You have like a 2 and a 2. And you can have like, I don't know where the other 2 twos are, but yeah, it can't be a 1 or 4, so it would be like a 3 and 3, for example. 3 and a 3. Three and a 3. So there's another like 3 3s and 3 2s. Yeah, like if all the 3s and 2s are on the outside, that would be another case where that works, right? Yeah, so if you think about the middle, right, there's, for example, the 5 4s, right? Like there's going to be 3 of them. Like it could be 1 here, 1 here. So there's going to be 3 of them, right? So then it has to be 2 of them in here, yeah? And the same situation with 3s, yeah? With the 1s. So there could be 2 1s here as well, or there could be 2 1s here. Obviously, if there's 2 1s here, you're done, right? Well, there's 2 1s here, and then a 1 and a 1. That's 4 1s, and still a 1 here. So you have 2 1s here, right? You have a 1. So if you have 3 1s, you're probably going with this as 1s. If you have 2 1s, you have a 1 here, 1 here, and a 1 here. There's one more 1. What is the 1 with? No, there's no 1s. There's 5 1s, right? There's no more 1s. No. And that's the question is where the 4s are at. There's a 4 here, the 4 here. That's already 4 4s. So if there's like a 4 here, okay, let's say there's a 1 4 here, yeah? Where are the 2s? The 2s, the 3s. So there's another 2 somewhere in the middle, right? Another 3 somewhere in the middle as well. And one of the So what goes here? What if like a 2 or a 3 goes here, yeah? Another 3 goes here. Then you have to have, there's 2 3s and 2 2s left to go, right?
Yeah.
So there must be a 2 3s or 2 2s in the middle, yeah, right? Yeah, so then that's the 3 3 group. That's the 2 2 group. Oh, wait, that's a 2. 1 2. 1 2 2. How many 2 are 1 2 2? I'm missing like a 2. 1 2 2. 1 2 3 4 5. Yeah. This has to be the 2s. Have the right number of stuff? Yeah. So this block has to be 3, 3, right? That block has to be 2, 2. This block has to be 4, 4, and then 1, 1 doesn't have a block. That's bad. Yeah. So basically, I guess once you do the first one, there is a change of order. Yeah, that's the problem. All right. So actually, once you take out the 2s, you don't actually care. Like that 4 might be a 3 as well. Yeah. Or like, yeah. So the issue is, maybe I can, to make the issue more clear, I can swap this 1 for this 3. Yeah. Okay. Okay, so what's the plan here? So the plan here is to remove the 2s, right? Because that's the repeated end block. And then you have to remove all the 2s, yeah? But the problem is once you remove the 2s, right? Oh no, you keep the 2s and you remove everything else, yeah? So you keep the 2s, yeah, you keep the m's, right? Remove everything else. Okay. Okay, so then what's left, right? What's left is sort of 4, 1, 3, 4, 4, 1, 1, 3, 3, 1, 4, yeah? So it's the lower case, right? Okay. Well, the problem is there's 4 1s. There's 5 1s, yeah? 1, 2, 3. There's no 1s here, so there has to be 5 1s, right? That makes sense? If there's 5 1s, yeah? Yeah. 5 1s, 3 3s, yeah? How many 4s? 4 4s. They're not in any order. They're not in any order. You know? There's 12 spots, right? Yeah. So the problem is when you try to use the induction hypothesis here, right? The problem is there's an odd number of 1s, right? So the 1s will pair up like this. Well, possibly you remove 6 things, you remove them all, right? But that's not guaranteed because you don't know how these are ordered, right? If you use your 6, you have to remove 6. You just remove the 1s and remove one of these. You're not guaranteed to be able to clean. You're not guaranteed to be able to clean 7 up with just one removal, right? So you can't spend all your removals on the 1s, yeah? Okay, and so in general, because there's so many things here, like I think you have to spend a certain number of removals on them. So the fact that there's so many 1s, but in the induction hypothesis, you don't get to choose which ones you remove, right? It just says you can do it for 12 things, yeah?
Yeah.
Okay, so the problem is you might end up with the 1 and the 3 going together, right? Like you might end up like this. Like it could be like 1 1 is a pair, right? 1 3, 3 4, right? And that's your 6, yeah?
Yeah.
You remove 6 from 12, yeah? So that's a problem because, right? The reason that's a problem is because 2 is in between 1 and 3, right? So they're not the 2 tallest people at that time anymore, right? But these are the shortest, clearly. These are the tallest, yeah. But these guys were the middle out of these guys, but they're not the middle out of the ones with the twos, right? The twos cut in between, yeah? There's a little bit of a cut again, yeah? Yeah. Okay, so once you realize that, actually, this obviously takes a lot less time to do than to explain, right? You don't actually have to explore each vague solve to understand that they exist. But like, once you're aware of this, I think it's relatively okay now, yeah? So basically what you need is, you need it, so you don't have any choice after you've removed it, right? So what you need to guarantee is you made the right choice with the twos, yeah? So basically what you need is, you need it, for example, if there's a twos here, right? You need there to also be a one, yeah? Because if there's a one, then you don't have this problem with an odd number of ones, yeah? Oh, sorry, I should also mention, yeah, you might want to strengthen the induction hypothesis a little bit as well. Yeah, so you might want to strengthen the hypothesis as well. So yeah, because see here, like here you don't know, like this could happen even if you had the right number of ones, right? Because it's okay. So I guess you need to say, you need a way to stop this from happening. Okay. So one way to stop it from happening is you strengthen the induction hypothesis to be that. I mean, it's very natural, right? If you think of it properly, like if this was normal, instead of having 5 ones here, right, you have 4 threes and 4 fours, yeah? All right? Like, what is it that you want? And this is basically what I've been saying the whole time. You can kind of do it with bottom, bottom, top, top, yeah? So you can do it as 1, 1, 3, 3, 4, 4, yeah? So basically what I'm saying is that the pairs that you make, right, after you remove the heights, yeah, you know, they have different rankings after you move it, but they're still in the same group that they were at the start, yeah? So they might not be the next two, but they're still in the top group, yeah? So basically strengthen it so that the pairs, basically, if you think of the top group as having like one color or something, you know, like the bottom group is another, it's like 3 colors. The pairs have the same colors, yeah? Form can be done within each color or group, yeah? So here you have 4 ones, 4 threes, and 4 fours. You can do a pair so that's 1, 1, 3, 3, 4, 4, yeah? And so that's the problem when you have 5 ones and 3 threes, right? It doesn't satisfy the hypothesis because you can't group 4 things together anymore in the middle. You know, there's a gap in the 2. Yeah, and the fact that there's a 2 here doesn't matter because they're relatively still the same, right? Relatively, they're still like the bottom from here is still going to be bottom overall, right? And the middle from here is going to be still above the 2 too, right? Yeah. Okay. Yeah, so that's basically it, right? So then what are you doing? So if you're looking at it, so now we can solve like, see, so what happens here, yeah? Let's look at this case. So this case doesn't work, right? But how can we make it work? Well, the thing is we don't have to choose the 2, 2, yeah? You see? So that was a 3, 4, 3, 2, 1, 2. So we don't have to choose the 2, yeah?
Mm-hmm.
People still here. I'm sure that their assignments are also picking up in intensity. I'm sure.
Yes.
Okay. Whew. So can you see like there's 5 things. There could be another thing that's repeated, right?
Yeah.
So can you see because there's like if there was a 1 here, then you're fine, right? But then you have 4 1s. But because there's no 1, then something else has to be repeated because there's 3 spots and there's 2 things left, right? Something else has to be repeated, and so 3 3 is the natural choice because anything else is easy to deal with, right? But look what happens when 3 3 is repeated, right? You take out the 3 3, and the 4 kind of acts like a 1, right?
Yeah.
Does that make sense?
Yeah.
So that works, you know? Okay, so the situation does get a bit more complicated. But in general, what's happening, right, is whatever pair you pick, right, you need it to be the right partition. You need to have the right number of things on the left and the right number of things on the right, yeah?
Yeah.
Okay. So, actually, Edwin found a really good way to express this idea. I should probably mention it. It's actually pretty nice. So, to express this idea, you can kind of understand it graphically, yeah. So basically, we're looking at the first n plus 1 spots, yeah. N plus 1 spots, yeah. Um, yeah, and I guess there's also n plus 1 groups, isn't there? Is it? There's n groups. Okay, and the question is which groups appear? So there's n groups, n plus 1 spaces, yeah? And the question is sort of how often do each group occurs, right?
Yeah.
So you may as well think of it as how does this work? So some group could occur 0 times, right?
Mm-hmm.
Okay. So in this case, in this sequence, we would say it occurs. So the 1 would occur 0 times, yeah? The 2 occurs twice, yeah?
Yeah.
The 3 occurs once, and the 4 occurs once, yeah? Right?
Mm-hmm.
Okay, so another way to represent this, and then the total amount, the total has to be n plus 1, right? Okay. The total has to be n plus 1 because n plus 1 spaces, yeah?
Yeah.
So maybe you can think of this, the x-axis, is like the x-axis is like which group you're at, right? So here it's like group 1. 1. group 2 all the way up to group n, right? That makes sense?
Yeah.
So once you got to the nth group, you basically, like whatever one you add up, you can add up the ones before it, yeah? That makes sense?
Yeah.
So how does this one work? It'll go like 1, 0, yeah? Yeah. And then you get to 2, it'll be 2, right? So it'll be 2, 2, yeah? And then when you get to 3, I probably should have labeled it 3. 3, right? It goes to 3. So it's 3, 3. Yeah? And then when it goes to n, which is 4, it goes to n plus 1. Yeah?
Yeah.
Does that make sense? Yeah. So basically what you need is, see, like if the 1 was at 1, right? If the 1 was at 1, then this would be 1, 1, and then the 2 would have made it go 2, 3, right?
Yeah.
So basically, like, the idea is if you exceed the y equals x line, that's when you have it right.
Oh.
Okay? Because that's when you have the right number of things on the left of it.
Yeah.
Okay? Yeah, so and obviously it ends up above the y equals x line because it ends up as n plus 1, right? Okay? So it does cross it starts off at 0, 0, right? Or it starts off at, sorry, 1. Well, you can assume there's no 1s for simplicity, yeah?
Yeah.
Because if there's a 1, oh, it could start off at 1, 1, yeah?
Oh.
You know? The point is, there's a finite number of points, yeah? And one of them is above the line. So there's going to be some point which first gets above the line, right? And to get above the line, you can't have slope 1. You have to have slope at least 2, right?
Yeah.
And slope at least 2 means you have to have a double of something, right?
Yeah.
Okay. So then that double of something is what you keep. Yeah? So here, see where it went above it? Well, it went above it right at the very end, I guess. So it went above it at the 4th one, right?
Yeah.
So it kind of did it so the 3rd one is the one just before it went above it, yeah? So if it was a 1, 1, then it'd be a 1, and the 2, 2 would be a 3 that's above it. Yeah, it's slightly confusing because at the end it's not the one, you don't remove that one. What happens if there's like a 2, 2 and a 3, 3? The 2, 2 would go like 1, 0, then 2, 2, and then 3, 3 would become, like if there was 2 3s, it would go 3, 4, right? And then it would end up above it. Yeah. So here you might not think it's 3. Yeah, so now you're removing the 3 3s, not for the reason that the 4's on the other side, right? You're removing the 3 3 because the 2 2's on the other side. See? You only need 2 of them to be left of it. Yeah? See, for the 2's, you need 1 thing to be left of it, right? You get rid of the 5 1s. So, but if the 2's don't have a 1, then you can't use the 2's, right? If the 2's don't have a 1, you can't use the 2's, so you got to use something else. Well, it has to be 3's in this case. And for the 3's, it's 1 further up, so you need more things on below it. You can't, like, one is not enough anymore because you've moved the barrier.
Oh.
Okay, so now conveniently there's two twos behind it, right?
Yeah.
So those twos serve the purpose, and so there's two twos behind it and 1 4 above it, and that's exactly right. Yeah.
Oh.
Yeah, and so the way the proof would go, if you wanted to make it in this nice little graph, you would say, because the graph of y equals x, there's like finite number of points. One of the points is above the line, right?
Yeah.
So therefore, there's a first point which exceeds the line, right?
Mm-hmm.
And that first point must be a double because it has to have a slope of 2 to even get above the line,
Mm-hmm.
right? And that's the double that you need to remove. You need to keep, you remove everything else, right? Because then you have the right number of things before and the right number of things afterwards.
Yeah.
Okay.
Mm-hmm.
And then together with the strengthened induction hypothesis, that solves the problem, yeah?
Yeah.
Yeah.
Oh.
Solve.
Big solve.
Yeah. Yeah, on some other stream, it's like fake solve 5. Look at this idiot.
Yes. Mm.
No, I'm getting a phone call.
Mm-hmm.
Hello? Hey, what's up? Oh, yeah, I mean, oh, okay, let me just explain this again. So, basically, maybe this will be like the write-up. Okay, let me just... Yeah, okay, so this is the induction hypothesis, okay? So, this is... so basically what we want to prove, so there's n times n plus 1 people, right? So then we sort them into n lots of n plus 1, yeah? In tallest to shortest. Yeah. So then there's like, yeah, so there's sort of maybe n sets of people, like A1 to AN. And these sets have like size n plus 1, yeah? Okay, so the claim is not only can you satisfy the condition, right? But you can do it in such a way that you're removing. So actually, if you say it that way, it sounds like the previous thing. But basically, the people that pair up in the end were also originally in the same set. Yeah. Yeah. So basically, if like two people pair up, if A B pair up, right, and A is in like AI, right, then B must also be in AI. Okay. Yeah, it doesn't matter. So basically, like for n equals 2, right? It's just the top two of the top three stay together, right? Yeah. So then that's the base case. And when you do the induction step, um, the the Yeah, so you can do it in blocks basically, right? And it's not so important. So the point is, if you can do it within the blocks, there could be like another whole, like there could be a pair sitting in between the blocks, and you kind of do it without worrying about it. You know what I mean? So like this block, like this group of people could all be shorter than this person, this pair, right? And this group of people could be all taller than that pair, yeah? Um, so, no, listen, okay. So if you have three groups of people, right? And all you know is that, like, this is the shortest, this is the middle, and this is the tallest, right? And you know that you can arrange it so that it has in pairs from each group, right? Yeah. That's what the induction hypothesis, right? Yeah, okay. But then imagine if you inserted a pair of people here, right? If you had a pair of people that were like all that were taller than all the short people and shorter than all the medium people, right? Then like you could do the same thing you did before. It wouldn't disturb the final arrangement, you know? Like the final arrangement will still have pairs where the there's nothing in between two people that are supposed to be paired, right? And that's basically the idea. So what we're doing is when we have the n plus one case, right? When we're doing the induction step, so we have the blocks, yeah? Yeah. So we don't get to choose the tallest people because they might end up in the middle, but we do get to see that there's lots of people that double up in the end on the ends. Yeah. And so but the problem is the height group that you keep here, right? You have to delete the height group elsewhere, and you have to basically delete everything else in the ends, right? Okay. So when you, yeah, yeah, yeah. So then you have to be careful how you do that because once you've done that, you don't get any more actions before you're inducting, right? You have to go straight down to the induction hypothesis, and this thing here is what I want to use as the induction hypothesis. Yeah. Okay. Yeah. And that's the pair that I'm trying to insert here. Okay. So the problem is if it was like the second tallest, right? If it was like 2 2, right? And there was no one, right? Then there would not be enough short people to make it three equal blocks. Yeah? There'd be too many. So the problem is you have five. So for example, in this case, there's four groups of five, yeah? So the next case is three groups of four, yeah? So you need there to be 4 4 4, yeah? Okay, so the problem is you don't get to choose that once you've deleted the end group and the other people of that height. Yeah. So you got to make sure you've already done it at the start. So the problem is, for example, if there's no shortest person here, right? And there's like five short people, then there's 4 and 3, right? It's not the right number. Yeah. Yeah. So it doesn't satisfy the hypothesis, right? The hypothesis you have three groups of equal numbers. Um, then then you can rearrange it so you can remove stuff so that the pairs end up in the same group they started in. Yeah, so if you have like no ones here, right? Because there's 5 ones to start with. If you have five, it's 4 lots of 5, yeah? So if you have 5 ones to start with and there's none removed, then there's 5 ones here, right? And that doesn't work. You need there to be 4 ones. So if there was a 1, that would be perfect. You just remove it and you're done, right? Because the hypothesis needs there to be 3 equal groups. If there's 5 ones, it'll be 5. If it's 3 equal groups of 4, yeah? Yeah, so you can't like, it doesn't make sense to label them now because the assumption doesn't hold, right? Yeah. Yeah. No. So the whole point is like the inserting thing is that if you have something here that's taller than the short and shorter than the median, yeah, it doesn't change the outcome. It'll still be paired with themselves. Yeah, like the shortest two here will still be shorter than those two, right? So they're not getting in the way of these if they're not mixed within them, yeah? Yeah, so the graph thing summarizes what we have to do to satisfy the condition, right? See, basically what happens is um, if you don't have a 1 here, okay, then you can't choose the 2, 2, okay? Because if you choose the 2, 2, it's going to be imbalanced and you can't do anything about it afterwards, right? You have to choose the 3, 3. And what makes the 3, 3 work is that there's enough stuff behind it, right? There's enough numbers lower than 3 because we need it to fill up the lower thing, right? Yeah, so I guess what happens is if you choose 3, 3, you're actually putting it over here, right? Between the tall and the middle, okay? And so what you need is because there's 10 things here, you need to remove 2 of them to make it 8, right? And then there's 4 above it. So there's 8 below it and 4 above it. Does that make sense? So if you're choosing 2s, right, it goes here between the short and the medium. If you're choosing the 3s, it goes in here between the medium and the tall. Yeah? Yeah, but it doesn't matter now because 1s and 2s are both shorter than 3, so you just need to be 8 of them. Yeah? Yeah. Yeah. Yeah, so it doesn't matter there's 5 1s now because you just need there to be 8 things here. So 5 is, you can just make sure that now there's only three 2s, right? Well, yeah. Yeah, exactly. So the way to get 3 2s is because you remove 2 of the 2s, right? So then 5 minus 2 is 3, and then you didn't remove any 1s, so there's 5 1s, so there's 8 things, right? And so the graph keeps track of this, right? Because you need, like, if you move up here, you need to remove more things, right? Here you only need to remove 1, up here you need to remove 2, next one you need to remove 3, right? Because you're getting further along in the partitioning. Hmm. Yeah. Yeah, so basically being enough. So if you kind of graph it, right? Like if you kind of graph it, like because there's no 1, it kind of like it starts off slow, right? If it went up, if there was a 1, then the 2 2 would make it enough, yeah. So one way to represent that is you can just kind of like the x-axis is how many like so it's like how many of each group there are. So the x-axis, the 1 is how many 1s there are. And the 2's, how many 2's there are? Yeah, exactly. It's cumulative on the y-axis. Yeah, how many there are, right? And so as soon as it goes above the y equals x line, that's when it's enough. Yeah, that's when it's just enough, right? And yeah, and it has, and when it goes above, it has to be a repeat, because to go above y equals x, you have to have a slope of more than 1, right? Yeah. Yeah, exactly. Yeah. Yeah, exactly. And there has to be a point which it exceeds the graph, because at the end it's n plus 1 and n, right? So that's already above y equals x. Yeah, exactly. If it starts above, we're done. Exactly. And so there's at any point it goes above, we're done. Then that's the point, right? Yeah. Yeah, exactly. And if you have more than a duplicate, if it goes above too much, it's okay, because if you have like if you have more than you need, the like if you have a triple instead of a duplicate, right? It saves you from killing it elsewhere, right? Because you had to hunt them down, remember? Right? Like when you killed the 2's, yeah? When you kept the 2's and the sides, you killed the 2's on the other bits, yeah? So if the 2 was on the side as well, it just saves you killing a 2 elsewhere, and you get a free choice to kill something else. So it can only help you. Yeah. I mean, yeah, or you can just incorporate it into like any time it goes above the y equals x line, because that's part of the going above the y equals x line. Yeah. Mm-hmm. Okay, yep. Enjoy the other class you have. I'm not enjoying it. Okay. Well, glad you enjoyed this one then. All right. Talk to you soon. All right. So that's maybe like our review of this. Do you think do you want to look at a write up? That's kind of like a write up already. Okay. Maybe we should move on. See, time is kind of long. Time is short. Yes. Would you like a break?
What are we doing next?
I'm explaining how to eliminate the odd case of the power of 2 question.
Oh. I had to break this thing.
Oh, I see.
While you were talking.
Oh, okay. Okay, let me put it on the board then. So 20. I don't think anyone's here anymore. So
Oh.
2015 IMO 2. So basically, A, B, B, C minus A C minus B equals 2M equals 2M 2 to the L, yeah?
Yeah.
And then we're basically assuming L equals 0. So if L equals 0, and A less than B less than C, yeah,
Mm-hmm.
then no solutions.
solutions. Hmm.
You can have like two. Honestly,
Hmm.
92.
I know. I've been locked.
Go.
Hmm.
All right. So what do we do with this? So I remember you did some things.
Yes. Some tunes.
So let's set this to be 1, yeah? And then you substituted C equals AB minus 1 into both 1 and 2, yeah? One becomes AB squared minus B minus A equals 2 to the n, right? 2 becomes A squared B minus A minus B equals 2 to the n, yeah?
Yeah.
And then you kind of did this sort of weird subtraction.
Yes.
AB outside of B minus A equals 2 to the n minus 2 to the n, yeah?
Yeah.
Don't know why you did it, but
I don't know, just cancel some stuff. So I just
Yeah. But it seemed to actually do stuff. Yeah, so like he didn't eliminate a variable, but he eliminated like
cancel weird things.
yeah. Okay, so is it clear from this that oh yeah, and we're considering this case by the way because we can show when they're equal it's 2, 2, 2, if two of them equals 2, 2, 3, and it's cyclic, so we can just assume they're ordered, and we can show that those two are not 1. Okay? So it has to be this one. If it was 1. Okay? And actually we also even showed that if C was even, right, it wouldn't work either. Yeah. So C would have to be odd, and A and B would have to be even. Right. Okay. So I guess the first claim is: can you see that the I'm gonna omit the subscript after a while. You know, it's all gonna be 2s. So can you see the 2s in A is the same as the 2s in B? Kind of a bunch of ways of seeing it. So how do you see the 2s in A the same as the 2s in B? Well, okay, so first of all, we know that L is, like, we know M is less than N, yeah? It's bigger than 0. Okay. Um, yeah, so for example, if A was like had less 2s than everything else, right? Yeah? Then look at this, look at the left hand side of this, for example. Yeah? See, this has some 2s, but not very many, and these all have lots of 2s, yeah?
Yeah.
So then the 2 component of this whole thing will just be that of A, right?
Yeah.
That makes sense? So then the 2 component of A will be 2 to the n, right?
Yeah.
But then the same argument here says the 2 component of A is 2 to the n. Right? They have to be equal. If the B was the smaller one, the same argument would apply, right?
Yeah.
Okay. So they have the same components in each of them, yeah? Okay. So what are they, yeah? Same components in each of them, what are they? Well, no, what I was doing. Let's see, so here it's clear that the component of the right hand side is m, right?
Yeah.
So that means v of a, right, times 2, there's 2 of them, plus v of a from there, right, plus v of, and I'm going to call it like b prime minus a prime, yeah?
Like, that's the B.
So when you cancel out of 2, I'll call the odd part b prime and a prime.
It's an odd part, doesn't it not matter?
Oh, it's odd minus odd.
Oh.
Okay. So here it's so here it's, yeah, so there's an odd odd. You take that out, right? And then that's what's left over, yeah? And that's equal to m, yeah? That makes sense? Yeah. And but m is also equal to well, so this is something. I should probably try to look and see how I did it. M is also from here equal to, if you take out the a's again, right? I don't like that. V and a plus v of, it's like a squared b prime minus a prime plus b prime, yeah? Oh. That makes sense?
Yeah.
Alright?
Yeah.
Yes?
I think.
I think.
So the a squared is just the 2va.
Mm-hmm.
And then that minus. Why where does the B prime come from?
Oh, because so I cancelled out like twos, right? So if you cancel two, you get m minus v, right?
Wait, that's this. Oh, that's from that.
Yeah.
Oh. Yeah.
So this is star. This is some two.
E is A plus B. Yeah. Okay. So
Mhm.
they're equal.
Yeah. So can you see how the second equation has to work, right?
Yeah.
So the second equation, see, the first equation is m has to have at least three v's, three new's in it, yeah.
Mm-hmm.
So three new a's in it. The second equation, like, see, there's two new a's here, right? In the a squared part, yeah.
Mm-hmm.
So you have to be able to get at least two new a's out of the second part, right?
Yeah.
Because there's three altogether, yeah.
Yeah.
So that means you have to have at least two of those coming from the a prime plus b prime.
Mm-hmm.
Yeah,
Mm-hmm.
that makes sense.
Mm-hmm.
Like,
Mm-hmm.
like two to the power of new, like two to the power of two new divides a squared b prime now,
Yeah. Mm-hmm.
and it divides like 2m minus v new, right? So it has to just divide a prime plus b prime. You know,
Yeah.
like if you think about it, if there's less, right, then that would be what's coming in,
Mm-hmm.
because it'd be like that amount times an odd number then, right?
Yeah.
Like think about what's happening with a prime plus b prime. It's an even number, right?
Yeah.
If it's got a single two in it, then that's going to be the new of all of that, yeah? Because the two is going to be a factor, and that's it. You understand what I'm saying?
Mm-hmm.
So like the question is, how many twos are in a prime b plus b prime, yeah?
Yeah.
Can you see there has to be lots?
Mm-hmm.
Because you know there's lots in a squared, right?
Yeah.
So if there isn't as many as there are in a squared, then or however many it is, it'll just come out, right?
Yeah.
But that won't be enough, yeah, because you need at least as many as there are in a squared to make it up to the first equation.
Yeah. Oh. Mm. Huh.
Does that make sense? So there's like, you need as many of the 2's as there are in a squared in a prime plus b prime. That's basically all I'm saying. For that to factor out, right?
Yeah.
And if it doesn't factor out, you're stuck because the top says there's 3 of them, yeah?
Yeah.
Okay, so if that's the case. Oh. So then what you know about that, so if there's as many 2's here as there are on that one, then there's at least 4, right? There's at least 2 2's.
Mm-hmm.
So one thing you know about like stuff is if 2 things is add together to be a multiple of 4, then when you subtract them, they're not a multiple of 4. Yeah?
Oh.
So if that's a multiple of 4, then that's not a multiple of 4.
Yeah.
Yeah? So that, and we know this is a multiple of 4, yeah?
Yeah.
And that's not a multiple of 4.
Yeah.
Then that's a 1, yeah? Yeah?
Yeah.
So this thing should equal 2 mu plus 1, right?
Mm.
Does that make sense? So this is supposed to equal 2 mu of A. I should even stop writing mu of A. I should just start writing mu plus 1. Okay, so that's 2 mu of A plus 1. Then basically, if you take the 2's out of that, but then if you look at this, mu of A prime squared B prime minus A prime plus B prime prime, yeah? Okay. And that's equal to 1. Mm. See, maybe I'm not doing node solution. What am I doing here? So if I apply the same thing to this, to 1, then n equals 3 mu. I'm not going to write a anymore. Mu just means mu of a. Plus mu of a prime b prime squared minus a plus b prime prime. What is this? This is not the claim I'm trying to make. Yeah, I think this is it. No? Yeah, so look, if you look at this equation, right? Oh, where's my question again? Yeah, so wow. Okay, so if you look at this last equation, right? for A prime and B prime to have lots of 2's in it, there has to be 1 and 3, right? Mod 4, yeah?
Yeah.
So if they're 1 and 3 mod 4, then A prime squared times B prime is going to equal B prime squared times A prime. Right? It's just equal to 1. Okay? So that means this A prime plus B prime prime, right, has to equal to 3 mod 4.
Yeah.
So it's because you want to get 1 minus 3 equals something that's only got 1, 2 in it, yeah? Okay? So that means if that only has 1, 2 in it, then this only has 1, 2 in it. Okay? So then n equals 3 nu plus 1.
Yeah.
But m also equals 3 nu plus 1. So n equals m.
Huh.
Yeah. I think in general we might be able to say something about how the n, m, and l's are related to the 2's inside of A, B, and C. And this may help us. Does that make sense? So let me recap the argument here. So we did some algebra, yeah? And from this equation, we see that the number of 2's on the right-hand side is m, yeah?
Yeah.
Number of 2's on the left-hand side is whatever's in A and whatever's in B. That's this 2, right? And it's got, since A and B are here as well, there's got another one from that, yeah? But then there's the 2 odd numbers that remains. They still might have some things when they're subtracted, yeah?
Yeah.
All right. So that's that equation. Yeah. Then we go to this equation here, 2. Like, there's obviously on the right hand side there's m 2, right? So that's this m, yeah? On the left hand side, there's at least one of these because there's an A in everything, right? A, B, yeah? Okay. Then where's everything else? Well, if you get rid of those 2's, then you get an A prime, B prime, right? B prime, A squared, yeah?
Yeah.
Okay, so that's this.
Yeah.
Okay. And then we're saying, because it's m, they're equal to each other, right? We need at least all this, we need this 2 thing to common as well. We got the 1, we need the 2. That has to come from here, right?
Mm-hmm.
For that to come from here, well, there's already 2 of these inside this one, right?
Mm-hmm.
This one also has to have that many as well.
Yeah.
Because if it didn't, this has to have as many as this, yeah?
Yeah.
So in particular, it has this many, right? In here. Because this many, and but A is even, so this many already makes this a multiple of 4, right? So this is 0 mod 4. If this is 0 mod 4, that's 2 mod 4, right? So that's equal to 1, okay? Yeah? And so if that's equal to 1, then this has to equal this plus 1, right? Because that's 3 plus 1, we get 2 plus 1, yeah?
Yeah.
So that means once you get rid of the 2's that you have to get rid of, there's only one more 2 that's formed by the odd numbers adding together,
Yeah.
yeah?
Mm-hmm.
Okay. So the odd numbers adding together, that's this expression, yeah?
Mm-hmm.
Okay, so that's equal to 1, okay?
Yeah.
Okay. So now we look at the only equation we haven't used, the first equation, right?
Mm-hmm.
And do the same thing, right? You can get rid of 3 nu from there, right? Once you got rid of the 3 nu, you're left with this term here, yeah?
Yeah.
A prime, B prime squared minus this, yeah?
Mm-hmm.
And because this, because A prime and B prime are 1 and 3, right?
Yeah.
Then you know that this is equal to 1, yeah? Mod 4.
Yeah.
So this was 1 mod 4 already, right? So this is definitely not 1 mod 4 because that wouldn't give you a 1, right?
Yeah.
There's actually a 3 mod 4.
Yeah.
So this must be a 3 mod 4. It's the same thing, right?
Yeah.
Okay. So then so then here it's also 1 because it's 1 mod 4 minus 3 mod 4.
Yeah.
Yeah. So then say n is equal to 3 nu plus 1.
Oh.
But n should be bigger than m, right?
Yeah.
But here it's equal to m.
Oh. Oh.
That makes sense?
Yeah.
Yeah, so I guess I thought more people would be here, but I guess I should have known better. There's something, I guess this was meant to just stimulate some ideas to keep going. But because this is definitely important because it sort of tells you sort of there's a relationship between the powers of 2 and the powers of 2 inside of A, B, and C.
Yeah.
And it's enough to actually resolve some cases. So there's no situations where they're all different where it's equal to 1.
Mm-hmm.
Of course, yeah. So I should probably write, we've already done 2, 2, 2. And they're all the ones with equal stuff. It's 2, 2, 3. Yeah.
Oh.
Mhm. Yeah. I'm suspecting the people who are still here are actually AFK.
Mm. Yeah.
Mm. So I guess what do you want to spend time doing? We can try to show the powers related, or we could go through someone's write-up of the other question.
Which
The fake soul fest.
Ah.
Or we could.
Oh, David's too.
Oh, David's here. Nice. He just joined to say.
Before you.
I feel like I phase solved this in my write-up,
Oh,
but I solved it on the board.
bruh.
Hmm. Oh. And so, would you be interested in doing that for the general case?
Sure.
Yeah. Hmm. You need another break?
Another break. Another what?
We don't have a break first. We have break fast. What do we need to do? Where are all these things? Okay, let's do it. Yeah, maybe it's easier to assume. So we know that if one of them's odd, they're all odd, yeah? If they're all
Huh.
concrete enough goal, what do you think?
Sure. Ooh.
I'll bring out the secret weapon. Oh. Oh. What is that? Celebration of gods.
Yeah. Nuts and nuts.
Nuts on the inside, nuts on the outside. All the nuts everywhere.
Yeah.
Any ideas? Let's be happy with not making too much progress. Yeah? We're in like marathon mode now. Not necessarily in sprint mode. Alright. You can do some obvious stuff from what we understood before. Remember, like for example, if the 2's in here are more than the 2's in here, then the 2's in here is equal to L, right? That's like a basic thing we figured out.
Yeah.
Yeah. So another way of saying that is if V of C is greater than nu of nu, yeah? Yeah.
Yeah.
If that's greater than both of them, yeah? That's one case, yeah? So actually, if it's greater than both of them, it actually has to also be even, right?
Yeah.
And if it's even, then one of the other two has to be even as well. And therefore, both of them have to be even. So that actually erases the assumption they're even, yeah? So if it's greater than, right, then it's this that makes the L, yeah? This is actually kind of a fun little game we can play, because it doesn't take much effort. But it helps you do logic So L has to equal nu A plus nu B, right?
Yeah.
Okay, well, if the C is truly the greatest, then that means B is the smallest here and A is the smallest here as well, right?
Yeah.
So then nu of A
It goes to A and down to B.
and nu of B is equal to M, yeah?
Yeah.
So the only thing we don't really know about is nu of C. But this is already a contradiction, yeah?
Is it?
Because L is the smallest,
Bruh.
yeah?
Oh. Even if it's the smallest, you still have the list 2's value, right?
Huh?
Oh, wait, no, that's not you. Oh. Yes, it is a contradiction.
Yeah, I don't know the symbol for contradiction. I'll just
Yes.
spam. Okay, so logically there's two other possibilities, yeah?
Yes.
It's less than, yeah?
Or equals.
Right. We can consider equals separately because that gets a bit weird, maybe. Who knows? So if it's less than, right, then L
Is 2.
equals nu of C, yeah? Maybe I'll just do a cross. A cross is generally something wrong, right? So A plus B is bigger than C, yeah? Alright, so I mean, this is kind of what I suspected the answer to be anyway, right? Just because I'm kind of hoping for like nu of C to be L, nu of A to be N, nu of B to be M kind of thing.
Yeah.
Because that's what happened last time. Yeah. But and also this is also difficult to get a contradiction or something because when you know C is less, C being less doesn't really help you here or there, right? You know? So the other case is if nu of C is equal, yeah? Now it's bigger than again, right? So that's part of the, so maybe that could be part of that case.
Yeah.
Yeah, so nu of C is equal. But then nu of A and B are N and M, yeah? And so M plus M is way bigger than, oh, it's equal to nu of C. So, but M plus M is bigger than L, right?
Yeah.
That's a contradiction,
Oh.
right?
Yeah.
Because there's an M plus M on this side, but L on the other side, yeah? That's no. So then what you're left with this, yeah? So not only is it V nu is less than A plus B, it's the smallest one, yeah?
Yeah.
So let's put our findings. So our findings are that nu of C is equal to L, yeah? That's pretty cool, don't you think? Yeah. And then, therefore, it's definitely less than A plus B, right? Because it has to be less. Otherwise, there'd be one more than L.
Yeah.
So that's consistent. Okay. Now let's try and find B and A, right? Yeah, so if C is L and that's less, right? Is it less or more? It's more. Yeah, it's more, yeah. We can't actually do anything about that. Yeah. So let's not be lazy because we know that condition can't give you the other cases, right?
Yeah.
So we can create the other cases.
Oh. Oh.
So for example, the two cases is whether nu of B is greater than L plus nu of A, right? Or not.
Mm.
Yeah?
Yeah.
That the nu of A, B is less than L plus nu of A. And then nu of B equals L plus nu of A, yeah? Those are the three possibilities.
The first one can't be possible, right?
Why is that?
Because that means B minus A is larger than C.
B minus A.
Yeah, like mu of B minus mu of A.
Why is that? What? It's,
We just move it around.
yeah, but why is that a contradiction?
Because that's bad. I don't know.
Oh,
Wait. Mu. Oh wait, so C is the largest, but mu of C might not.
yeah. Okay. So one of these conditions will lead to glory,
Oh,
and one of these conditions will lead to contradiction.
I don't know.
Okay, what happens if it's equal? Then B is still bigger than A, right? So whenever B is bigger than A, we know that A is N, yeah?
Yeah.
Whenever B is bigger than A, we know A is N. Whenever L plus VA is bigger than B, we know that B is M, yeah?
Mm-hmm.
We also know B is greater than C if B is equal to C. Yeah, the last one can't help us here. 5. B is greater than A. So what's wrong with VB equal to N plus L? Is that something horrid? I just put a crossword in my notes.
Huh.
Something so horrid. Oh yeah, of course, because if a VB was equal to N plus L is AC, right?
Mm-hmm.
So B and AC both have N plus L. That's bigger than M, yeah?
Yeah.
Cross. So I think that the same would apply if B was greater than that, right? Right. Yeah. If B is greater than that and that's equal to n, yeah, then there'd be more n's than n. There'd be more n. There'd be an n on the left-hand side of 2. Yeah.
Yeah.
Because there's n here, and then there's B also. The n is meant to be bigger than n, so that's contradiction. Yeah.
Oh.
Yeah. And what we're left with is the only condition we can't draw any other conclusions, but we also already got the conclusion we want, right? Yeah.
B equals M.
AB equals M. I like those theorems where you don't have to remember the proof because it kind of reproves all the steps that's needed, if that makes sense. Like if VB equals M, it's obvious it's got less 2's than AC, you know?
Yeah.
So you don't need to write that up. VB equals M, yeah?
Mm-hmm.
So if you kind of spot the pattern, it looks like the goal could be
B equals N.
yes, sirree.
Wow.
Yeah.
Huh.
And so now, and if you look at the pattern again, it's not like we're going to be able to use the assumptions we had before to proceed, right? We need new assumptions. So the question is whether BC and how BC compares to A, right?
Yeah.
So whether M plus L is bigger than A, equal to A, or smaller than A, right? If it's bigger than A, then A is N, right? Yeah.
Mm.
If it's equal to A, then A is not N, yeah?
If it's equal to A.
It has to be less.
Yeah. Yeah.
Unless
It's like something weird. Yeah.
Yeah.
I don't quite know.
and if it's less than A, if it's less than A, it's interesting because then M plus L is equal to N plus L is equal to N. That's equal to A. And here we have M is greater than N, no. And here it's less than N. Oh. Do you think these are legitimate cases? N plus L equals N.
plus L.
There's two cases that definitely don't. I'm trying to eliminate one of those cases. What if we try to do what we did last time?
Last time.
I'm stuck.
Ooh.
Okay, so last time we solved 3 into 1 and 2, yeah?
Oh, yes.
So then now we have C equals AB minus 2 to the L, yeah? A B is AB squared minus 2 to the LB. Minus A equals 2 to the N, yeah? This pen might be at its end. And then it's A squared B minus 2 to the LA minus 2 to the M, right? That's what we had before.
Yeah.
So for some reason, I'm very tempted to subtract L times the second one from the first one.
L times. An interesting position.
Yeah, it's kind of like what you did
Yeah.
with L equals 0.
Yeah.
So if you try to subtract L times that from the first one, yeah, what would you get? You get not L times 2 to the L, obviously, yeah?
Yeah.
So you get AB squared minus 2 to the L A squared B, okay, minus 2 to the L B, and the A's, no, the B's cancel, yeah?
Yeah.
And then you get some weird thing with A's. So it's actually like plus 2 to the L minus 1 times A, right? Equals 2 to the N minus 2 to the M plus L.
Isn't it 2 to the L squared? 2 to the 2L.
Which one?
The A.
Oh, good. Yeah, you are here. You are present.
Yes.
Perhaps I'm not present. Okay. All right. So I guess this would be great for exploring this condition, right?
Yeah.
See, because if n plus l equals n, right,
Then that should be.
that's 0.
Yeah.
So what happens if it's 0? Then there's a common factor of a, yeah?
Mm-hmm.
Right?
Yeah.
you get b squared minus 2lab plus 2 to the 2l 1. Yeah. Contradiction.
Is that a contradiction?
Indiction.
Is it?
Yeah.
Wait.
Actually, we might even need to. Might even be able to use this one. It might still be true that they equal in the end, right?
That's
It's
just quadratic in 2 to the L.
The integers, yeah.
What are integers?
So integers are like
Mhm.
whole numbers where, like, if a whole bunch of them are even, the other thing has to be even too. So it can't go even, odd.
Oh. Is B even? All B is even. Ah, yes. Yes.
Even, odd, yeah.
Yes.
Or even, one, odd.
Okay. So,
So this one's a contradiction. So v of a is not greater than n. V of a is less than or equal to n.
wow.
It's almost an equals.
Mm,
This is still possible, I guess.
let's try it. Yes. Yes.
Yeah, actually, v of a equals n here is actually confusing, isn't it?
Hmm.
Oh no, it's alright. Wait. V of a is equal to n. So v of a is equal to n, right? And there has to be.
And
So there must be. There's n here, right? And there's n here. Yeah.
2 to the L times B.
Has to also have a 2 to the n. Yeah.
Yeah.
So L plus m is bigger than n.
L plus M is bigger or equal to N.
Yeah. So
O
it's
plus
bigger
M.
than or equal. So it's bigger than or equal to n.
Right, that one.
So that's the first one is bigger than n, right? And if the second one is equal to a, but less than n.
Which is not right. Right?
Yeah, because the second one is not equal to n.
Ah. Wait. Oh, that's
Yeah, that's hectic.
bruh. Ugh.
So what happens if it's less than n? Is there something ridiculous happens to? V of a is less than n. Oh, here actually is also. Can you see that the right hand side is m plus l, right? If yeah, well, we don't know if n is bigger than m plus l. Do we know if n is bigger than m plus l? So one of them, m plus l, is bigger than n actually.
And one of these are
Oh, actually, yeah. Check it out. So if m plus l is bigger than n, right?
Yeah.
Then the right hand side is n. Yeah. So it's n. Okay.
No.
If it's n, well, the left hand side has an a. Yeah.
Yeah. So A goes into N.
Yeah.
Mm.
Yeah. And once the a goes into n, right? This is odd, right?
Oh.
These are even. Yeah.
Wait, that doesn't show anything. Wait, what does that show?
Oh, we already have it. It shows v of a equals n.
Oh.
Yeah, I think that's originally what we had. That's what that was what we kind of want actually. So if that's what we want, then we should be considering the last case,
Yes.
where m plus l is less than n.
Wait, m plus l is greater than
So here is m plus l is greater than n, right?
yeah.
Which gives you VA equals n. That's what we want, right?
Oh, yeah.
This one is m plus l is
Okay.
equal to VA, which is less than n.
Yes.
Yeah.
Yeah. And that side would be m plus l.
Yeah. So that happens. That happens here.
Oh.
Yeah. This is less than n. That's m plus l. Oh, so the right hand side here is clearly just a.
Yeah.
Oh gosh. Odd plus even.
Yeah.
There is another way. Maybe we could use that equation. Okay, so what if we put the AB squared equation? Yeah.
Yeah.
What if we put the 2 to the L on the right hand side?
2 to the L.
What? 2 to the L of what? What? 2 to the L A squared B. A squared, AB squared. Yeah. AB squared equals, AB squared minus A equals 2 to the N plus 2 to the LB. How do you get that? Just like put it on the right hand side. Wait, how do you cancel stuff? Cancel? No. What? No canceling. Okay, that equation, yeah.
Oh, that I thought it was the one down there. But that's also the AB squared one.
2 to the LB, yeah.
Yeah.
Wow, it doesn't help that much. Yeah, I guess this was the same what we had before. In a more obvious way.
Mm-hmm.
Yeah, so V of A is either equal to N or less than N, but in either case, it's less than or equal to N plus L. So N is greater than or equal to N plus L. N is, wait, no, it's N is greater than or less than N plus L.
Bruh. Greater than or less
I
than. Whoa.
guess it's not equal to N plus L, yeah? N is greater than N plus L. Okay, so let's assume V of A is equal to M plus L. Then you could divide the stuff by the m plus L2s. You get a prime b squared minus b prime minus a prime equals 2 to the n minus mu. Okay. How many examples? Do you think we got all the examples? That would guide us. Hmm. Sometimes it's hard to prove because it's not true.
Hmm. Hmm.
Ugh. What if you just straight up subtract them? Ugh. A, B. Outside of B minus A minus 2 to the L, B minus A plus B minus A. Is 2 to the N minus 2 to the N. So now the right hand side is obviously M. Left hand side is a factor of B minus A. Yeah. Oh, but there's no, the B and the A are not the same anymore, yeah? That's the problem. You need to times it by 2 to the L to make it the same. Times it by 2 to the L. Make it the same. Then yeah, it's obviously less. Oh. Oh, no. Could it be that sinister?
My.
What if you times the first equation by 2 to the L? No, does that even work? Then it'll be like A, B, 2 to the L, B minus A. Is that, can you achieve this?
Wow. Ooh. Ooh. Oh.
Huh?
Yes.
No, yes.
No.
So the one problem is this B is coming from the second equation,
Bruh.
whereas the other two B's come from the first equation.
Oh.
Yes. So what you get instead of 2 to the LA.
Oh.
And they cancel. And you get that. And oh, and don't always get minus 2 to the LA. No, they do cancel. Alright, just in case, what happens? A, B, 2 to the LB minus A. 2 to the LA is cancelled. Minus B. Minus 2 to the 2LB. 2 to the N plus L minus 2 to the N. Yeah, this is not good.
Huh.
Oh, now. N is bigger than M plus L. That's what we should do. We may have to resume this another time.
Yes.
Nobody's left.
Everyone's dead.
Remember last term, by week 9? This is week 9 already.
What happened?
Well, no one was left by week 9.
Oh. Wait, on the Monday class or the Sunday?
Monday.
I don't even remember what happens.
We did like projective geometry until
Oh. And everyone left.
yeah.
Oh.
Alright, so the conclusion is the V of A, the new thing, is less than or equal to N.
Yes. Correct conclusion.
Yeah. Maybe it will do what we need it to do. Yeah, I guess another thing you could try and do is when it's when L is 1, yeah? That's another thing that could be done. L is 1.
Yes.
So I wish I remembered when we did VB equals M whether it was even or not. I guess we're assuming it's even, but the question is whether we needed to assume they were even.
Yeah.
Like in this case, when M plus L is equal to V of A, then V of A is even here. A is even. And L is C and V are even there. And if V of A is equal to N, then they're all even. If V of A is equal to M plus L, it's even. Oh, you ate the chocolate. And some more.
What boxing gifts? I'll have like one chocolate. One. Oh, that's not one.
One chunk. Anyone's still here? Oh yeah, sure.